Okay, for number 35, we have a silver ion complex with ammonia. And they tell us that they want us to determine the amount of free silver left over after it's reached equilibrium. If 0.2 moles of silver nitrate's dissolved in a liter of ammonia, and the concentration of ammonia at the end is 2 molar. Okay, so when we have problems like this with KFs, we're going to need to use an ice table remix. Okay, so first we write the equation for our complex. So I just took the ions that make up, or the individual components that make up the inside of the brackets, and added them together. So I have the silver and the 2 ammonia forming the complex. And any KF reaction should look like this. Okay, and so then we're going to use an ice table. And put in our information. So what I took away from this part of the silver nitrate is that our concentration of silver ions that we start with is going to be the 0.2 moles in the 1 liter. Because the silver nitrate is soluble, and it's just going to split apart into ions. So we'll get 1 mole of silver out for every 1 mole of silver nitrate. Okay, so that's our starting concentration of the silver. Pop that in there. And what they really want us to figure out is, what is this equilibrium amount of silver left over? Okay. The other information they give us is the equilibrium concentration of ammonia, which is that 2 molar. And then they don't give any other excuse me. Okay. They don't give any other information. Okay. So this is where the remix part of our table comes in, because we don't really have enough information to do a traditional ice table setup. We don't have initial ammonia concentration, we don't have initial complex concentration. But one thing we do know is that our KF is really big. Right, 10 to the 7th, that's superproducts favored. So we can assume that most of our silver ions, if not all, end up in this complex. So we can bring this number down. Okay, and this is just because KF is so big. Okay, and then once we do that in our ice table, we have a whole equilibrium row set up. So we can just go ahead and plug that into our KF expression like we would for a traditional ice table. So our KF expression is going to be the concentration of our complex divided by our concentration of silver ions times the concentration of the ammonia squared. Okay, so don't forget the coefficients when you set this up. And so we can plug in, and we have 0.2 molar divided by X times our ammonia concentration at 2 molar squared. And then we can set this equal to KF, which is the 1.5 times 10 to the 7th that was given. Okay, and then after the algebra, we find that X ends up being equal to 3.3 times 10 to the negative 9th molar silver ions. So that's what's left over. Okay, so it's a really small amount, which makes sense because we made that assumption that pretty much everything would go to the complex. And so this would be the tiny amount that's left over. Okay, so pretty much any problem with the KFs, you're going to use this assumption where you bring the silver or the ion concentration down to the complex. So here, number 36, they want us to think about oxidation states. And so we have this garnet stone, and they tell us the oxidation state of iron, but they're asking us about oxygen. And so here I've written out our preferred oxidation states for different elements, and I've written them down so that they're in increasing strictness. So if we think about things from the perspective of oxygen, only things written above it in this table can get it to change its oxidation state. Okay, so only if there's an alkali metal, an alkali earth metal, fluorine, or hydrogen that force the oxygen to change its oxidation number. Otherwise, oxygen is always going to be -2. And if we look here, none of these other three elements are any of those above oxygen on the list of preference. Okay, there are no other VIP elements to get oxygen to change. And so the oxygen's just going to be -2. It's kind of a lame problem, not going to lie. Okay, so the infamous Rick T. Cat makes this new complex, Nitnium LOL. And he found out that it absorbs light with an energy of 292.76 kilojoules per mole of photons. And he wants us to pick what color it looks to our eyeballs. Okay. So just as a reminder, here we have the equation for relating the energy of light to its wavelength. Okay, and so let's just remember what goes into this equation. So energy is just energy. We put it in as joules per photon. Okay. H is Planck's constant. It's on the data sheet. 6.636 times 10 to the power of -34 joules times seconds. And then for C, we have the speed of light, which is 3 times 10 to the 8th meters per second. And then the wavelength that we calculate will pop out in terms of meters, because we have that meters in the speed of light. Okay, so the energy that we need is in joules per photon, but the energy that we're given is in kilojoules per mole of photons. So I've gone ahead and written out this conversion where we start with our given energy, and then we use Avogadro's number to convert from a mole of photons to individual photons, and then a conversion just simply to get from kilojoules to joules. And so when we go ahead and solve this, we'll end up with, so we get 4.86 times 10 to the negative 19 joules per photon. And this 10 to the negative 19th is very common for the energy of photons in the visible spectrum. So seeing that number can be nice and comforting. Okay, so we have our energy for a single photon, so we can put that into our E equals hc over lambda equation. We end up with this setup where we have our energy equal to Planck's constant times the speed of light divided by the wavelength, which is what we care about, because we can then relate that to color. And when you solve this, you get that lambda is equal to 409 nanometers. Okay, so we have that number, and so now what we do is we take out our data sheet and we look for where 409 nanometers falls on the color wheel, and we see that this is violet. Okay, so that's the color absorbed. But it's asking for the color that we see. And so on the color wheel, what we'll do is we'll look across, because that will give us the complementary color, or the color that we see if we remove all of the purple. And that color is yellow. So the answer here is C. Because we see yellow. Okay, so we have this Voltaic cell diagram to use for the next two questions. And we have some true or false statements to answer, but let's just think about what's going to happen with our cell before we, get into answering those. So we have gold and lead as our two metals in our redox active species. And so I've written out both of their reduction half reactions here and the potentials from the table. So one of these is going to need to be reduced and one's going to have to be oxidized. And so we may as well pick the one that likes to be reduced as the side for the reduction. And that's going to be the gold because it has a positive reduction potential. And then what we'll do is we'll flip the lead equation to make it an oxidation instead. And then when we flip this equation, because we're writing the reverse of it, we will reverse the sign of its potential. Okay, and now we're not going to use this at all. To get our overall cell potential, under standard conditions then, we will just add those together. And we get this cell potential of positive 1.816 volts. Okay, so now we know that the lead side is going to be our anode. And the reaction that will occur is the lead from the electrode becoming lead ions and spitting out 2 electrons. Okay. So we'll end up forming more lead ions. That's hard to read, I'm sorry. And we'll spit out electrons. And so what happens then is the electrons flow through the wire. And they come down into the gold side. And then the gold ions in the solution pick up those electrons to form the solid gold. Okay, so we'll end up forming some more gold on that electrode. Okay, and so electrons are being dumped into this gold side, so it's becoming more and more negative. And because of that, the sodium from the salt bridge is going to flow down into that solution to neutralize that charge. And because electrons are being sucked out of the oxidation side, it's going to become more and more positive or less negative. And so the nitrate will flow toward that. So the anion flows toward the anode, and the cation flows toward the cathode. Okay, so now that we've thought about our diagram, let's read through these statements. So the first says, electrons flow through the wire from the lead electrode to the gold electrode. That makes sense, that's what we predicted. 2 says, sodium cations in the salt bridge will migrate toward the cathodic compartment. That's also what we said. 3, the gold electrode serves as the anode. Nope, it should be the cathode, because that's where the reduction is happening. 4, the mass of the solid lead electrode will decrease over time. And that's also true, because the solid lead is breaking down into the ions, so it's kind of disintegrating, whereas we're depositing more gold on the gold electrode, and it would become heavier. Okay, so then the correct answer here is just D. So it does help to, make your own predictions about what goes on before you look at the statements. Because sometimes when you look at the statements, they kind of twist your perspective of what you expect. Okay, this next problem is asking us to think about the same voltaic cell, but they want us to figure out what potential we would actually read from it. And so this is going to be different from the standard condition potential that we calculated on the previous problem, because we're not at standard conditions. To be at standard conditions, we would need to have 1 molar of both solutions, and we clearly don't have that here. So we're going to have to use this equation. And so let's go ahead and remind ourselves what half reactions we're working with. So we have these equations and that overall potential under standard conditions. So when we think about calculating the non-standard potential, we can go ahead and just use that 1.816 volts for our standard potential. We'll have minus 0.0592 from the equation, and divided by N. So N is our moles of electrons transferred, and this is where our half reactions become useful. So we can see here that between the two half reactions, we don't have the same number of electrons transferred. And so rather than picking one or the other, we're just going to make sure that they match up by multiplying that top equation by 2. And then both reactions would have 2 electrons being transferred. So our N is going to be 2. And now we need to figure out what Q is going to be. So we know that we think about Q similarly to an equilibrium expression. We'll use the same kind of setup. We'll have Q is equal to products over reactants to their coefficients. But we don't have an overall reaction yet, but we can figure that out. So we can just combine our 2 half reactions. We'll have 2 gold ions. Those are in solution with the lead solid, reacting to form lead ions in solution and 2 moles of the gold solid. So now we can use this reaction to figure out our Q. And so we're going to have our aqueous products, which will be the lead ions, just to the power of 1, divided by concentration of gold ions squared because of that coefficient. And so we can put in the concentrations right underneath the beakers up there. So we're going to have 5 molar divided by 0.0002, oops, an extra 0, sorry, molar squared. We'll punch this in to get Q. And then we get that giant Q of 1.25 times 10 to the 9th, and we can plug that in to our equation above. And now we've filled out all of the pieces of that equation, and we can solve for the overall potential under these conditions. And when you plug this in, you get 1.564 volts. And this is lower than your standard potential, and that kind of makes sense when you consider that we have a really big Q. Because that would tell us that we probably have too many products. And so we're going to shift left. And a shift left is always a decrease in potential because you're becoming less spontaneous. And a shift to the right is more spontaneous and an increase in potential. Okay, for number 40, they want us to figure out what the KSP for barium sulfate is given these individual delta G's of formation. So whenever we're doing a KSP problem, we're always starting with our solid and breaking up into ions. That's always the reaction we write. And so we can relate these delta G values to KEQ, or KSP in this case, with this reaction here. This is on the data sheet, but it gives us a direct connection to delta G and KEQ. And since we have individual delta G's of formation, we'll just do the delta G's of formation for the products minus reactants to get the overall change in delta G for the reaction. And you can do this for delta G, you can do it for delta H, and for delta S. Okay, so we can just go ahead and set this up, where we'll have our overall change in delta G, or in free energy, equal to the value for the barium ions plus that for the sulfate ions. So we'll have negative 560.66 kilojoules for the barium plus the negative 741.99 kilojoules for the sulfate. Now minus the products, which is just the barium, minus the reactants, which is just the barium sulfate. So negative 1353.1, and all of these numbers were in kilojoules per mole. So products minus reactants. And then we're just going to punch this into our calculator, being careful to pay attention to the signs. And we'll get 50.45 kilojoules per mole. So we have a positive delta G of this reaction, so non-spontaneous, which kind of makes sense because our solubilities usually are really unfavorable. That's why we call them insoluble. Okay, so now we have our delta G, and we're going to plug into this delta G KEQ equation. So we'll say 50.45 kilojoules per mole is going to be equal to negative R. And so the R we're going to use is the one with joules in it, and I'm going to write it in as kilojoules. 8314 kilojoules per mole Kelvin, which brings us to temperature, which we need to put in Kelvin, as per usual. We never use Celsius. And then we'll have the natural log of KEQ. And so all we're going to do is now divide by everything except the natural log, and we'll end up that the natural log of KEQ is equal to negative 20.36. And so to get KEQ, we'll just do e to the power of negative 20.36. Which is equal to 1.43 times 10 to the negative 9th for our KSP. Let's answer choice B then. And that K makes sense. It's really small, which would correspond well to a non-spontaneous reaction because it's not products favored.